In this video, I'm going to discuss converting between binary, octal, hexadecimal, and decimal. Let's start with something you should already know how to do, and that's to convert between binary and base 10. This is a binary number. That's what that little 2 there means, base 2 or binary. And of course, you know how the place values work. That's the 1's place, the 2's place, the 4's place, the 8's place, the 16's place, 32, 64, 128, and so forth. Every time I go up in place value, I multiply by 2, right? Or another way of thinking about it is double. Another way of thinking about it, of course, this is the 2 to the 0. This is the 2 to the first. This is the 2 to the second. 2 cubed, and so forth, right? 2 cubed is 8, of course. 2 squared is 4, and so it works that way as well. Anyway, if I want to figure out what this number is, I just add up every place I have a 1. So I have a 1 in the 16's place. I have a 1 in the 4's place. 16 plus 4 is 20. A 1 in the 2's place. That's 22. So this number is 22 in base 10. And I could do the number underneath it as well. I have a 64. That's a 1 in 64's place. I have a 1 in the 8's place. I have a 1 in the 2's place and a 1 in the 1's place. So that's a 1. So that is 75, I believe, in base 10. And I think you've done this before. So this is nothing new. All right, let's move on. Let's convert from decimal to binary, and let's use the process called successive division. I wouldn't necessarily do it this way, but you should be familiar with this process. So I want to figure out what 22 is in base 2. So that's why I am dividing by 2, because I want to convert it to base 2. Again, I'm starting with the base 10 number and I want to go to base 2. So the way you do this is you say, well, how many times does 2 go into 22? It goes in 11 times with 0 left over. So I'm going to keep track of the remainder here. This is 0 left over. Then I have to bring down the 11, and I'll just repeat this successive division. 2 goes into 11 5 times. Well, that gives me 10. So the remainder is 1. Now I'll divide 2 into 5. That's 2, right? 2 times 2 is 4. So again, I have a remainder of 1. 2 goes into 2 one time with 0 left over. So remainder is 0. 2 goes into 1 0 times with my remainder of 1. So you keep going until you end up with a 0 here on top. So in other words, 2 goes into whatever it is 0 times. Then if you want to figure out what the number is, you read it from the bottom up. So this number is 1 0 1 1 0. That is my base 2 equivalent using the process of successive division. Now I wouldn't necessarily do it this way. I would do it just by, and we've done this in class before, just by writing out a bunch of dashes, with the place values on them. In other words, I know in binary that's the 1's place, the 2's place, the 4's place, the 8's place, 16, 32, 64. Well, actually, that's farther than I need to go. I only really need to go to the 16's place because I'm only talking about a 22 here. So I know that I'm going to have a 1 in the 16's place. That is going to give me 6 left over, right? 22 minus 16 is 6. So that means I have 0 here. Then I have a 1 in the 4's place. That gives me 20 so far. 16 plus 4 is 20. I need 2 more to make 22. And there we go. That's 2 more to make 22. And I have a 0 in the 1's place. So this is how I would do it. I would not use the process of successive division. But so you know you can do it that way if you like. Anyway, my number in base 2, you can see they're both the same here. This is the same as this. Of course, it doesn't matter which process you use, but once again, I prefer this process. All right, let's keep going. Now let's talk about converting between octal, or base 8, and decimal. And I'm going to use the process of weighted multiplication. It's the same thing that we did when we converted between binary and decimal. I just think of each number in its correct place value. This is the 1's place. This is the 8's place. This is octal now. So every time we go up, we multiply by 8. This is the 8 times 8, or 64's place. right? Let's think about it another way. This is really the 8 to the 0. Anything to the 0 is 1. This is 8 to the first power, which is 8. This is 8 to the second power, which is 64. If I had another digit, it would be in the 8 cubed place. 8 times 8 times 8 is 512, I hope. Okay. But I don't have anything here, so I don't really need to worry about this place. Anyway, let's see what this number is. I have a 2 times 64. 2 times 64 is 128. So this 2 is really 128. I have a 5 in the 8th place. 5 times 8 is 40. And I have a 6 in the 1's place, so that's just a 6. And so if I want to convert this number to base 10, I just add all of these up, and that gives me 174 in base 10. So the base 10 equivalent of this octal number is 174. All right, let's just do one more real quick. So I have a 0 in the 1's place. I have a 7 in the 8's place. I have a 1 in the 64's place. Okay, 1 in the 64's place, that's 64. 7 in the 8th place, 7 times 8 is 56. And then I have a 0 in the 1's place. Well, that's just a 0. And if I add all these up, that gives me, what is 64? That gives me 120. And that is my base 10 equivalent to this base 8 number. Now, another thing that you might want to notice, of course, is that in binary, you only had 2 possible digits, 0 and 1. In octal, or in base 8, how many possible digits do you have? Well, you have 8 possible digits. They are 0, 1, 2, 3, 4, 5, 6, 7. Notice there's no 8. This is the only 8 possible digits that you can have using octal, right? This is 8 possible numbers. 1, 2, 3, 4, 5, 6, 7, and 0 is 8. All right, let's move on. Here is an example of going the other way. Now I'm going to go from decimal, from base 10, to octal, and I'm going to use the process of successive division, just like when we went from decimal to binary. And I wouldn't necessarily do it this way, but this is something that you should know how to do. So I'm converting into base 8. That's why I'm dividing by 8. And I'm going to see how many times 8 goes into 174, which I believe is 21 times. Now I have a calculator right next to me here, so I'm going to punch this in as we go. So 8 times 21, let's see what that is. 8 times 21 is 168. So that means that I'm going to have a remainder. This is all about calculating remainders. So I'm going to have a remainder of 6. All right, so now I have to do 8 into 21. 8 into 21 just goes twice. 2 times 8 is 16, so that means my remainder is going to be 5. And finally, I do 8 into 2. 8 into 2 goes 0 times, and you keep dividing until you get 0. So 8 goes into 2 0 times, and my remainder is 2, and that is my number, and you read it from the bottom up. So the number is 256 in base 8, and of course you can check just to make sure this worked properly. I know that I have a 6 in the 1's place, which is 6. I have a 5 in the 8's place. Remember, this is the 1's place, the 8's place, the 64's place. I have a 5 in the 8's place. 5 times 8 is 40. I have a 2 in the 64's place, so that is really 128. And if I add all of these up, that comes out to 174 base 10. So it in fact worked. 256 base 8 is my number. There you go. Finally, it's time to talk about base 16, also known as hexadecimal. Hexadecimal is actually used a lot in programming, and if you get into programming, you will definitely see it and need to be familiar with it. All right, I'm going to use the process of weighted multiplication. This time I'm in base 16, so this is the 1's place, or 16 to the 0. You can think about it that way. This is the 16's place. It's 16 to the first power. This is the 256 place. Well, how did I know it was 256? Because it is 16 to the second, or 16 squared, which is 256. So let's see what this number is in base 10. I really have a 1 in the 256 place, which is 256. I have a 2 in the 16s place, which is a 32. Oops, 16 times 2 is 32. And I have a 5 in the ones place, so that is just 5. And if I add these all up, which I will do with my calculator, 256 plus 32 plus 5 gives me 293. I'm adding all these up. 293 in base 10. That is the equivalent to this base 16 number. All right, let's do one more. Now, this is a little bit strange. I have, again, the ones place and the 16s place. But what is this business with B? Well, in base 16, of course, you're going to have 16 possible digits. They are 0, 1, 2, 3, blah, 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 all the way up to 9. Well, that's only 10 digits. So in hexadecimal, they decided to use the letters A through F to designate the numbers, the digits past 9. So A, B, C, D, E, and F represent the digits 10, 11, 12, 13, 14, 15. All right, so let's go back to my BC here. Now a B in the 16s place, a B is really 11. So that means I have 11 times 16. 11 times 16 is 176. So this B right here is 176. And then I have a C in the ones place. Well, a C is a 12. Okay, so 12 times 1 is 12. So I have 176 plus 12 is 188 in base 10. So BC is 188 in base 10. All right. Hey, we're almost there. Hang with me. So let's do one where we will convert from decimal to hexadecimal, and I'm going to use the process of successive division. If you stay with me till the end here, we will do a shortcut for all of this. So I'm dividing by 16 because I want to convert to base 16. So 16 into 293 goes 18 times. 18 times 16 is 288, so that will give me a remainder of 5. Then I will do 16 into 18. 16 into 18, of course, just goes once, and that gives me a remainder of 2, right? 18 minus 16 is 2. Then finally, 16 into 1 goes 0 times. Hey, I'm done. I just have a remainder of 1, and again, you read them from the bottom up. So this is the number 125, which you already knew in base 16. And just to check, of course, I know that this is the ones place, the 16s place. The 16 times 16 is 256. So this is really a 256 plus a 2 times 16, which is 32, plus 1 times 5 is 5. And if I add that all up, I get 293. So it in fact works. 293. All right, in base 16. Oh, sorry, in base 10. So this is just my check here. This is the actual value. Again, hang in there. The next slide, I'm going to talk about a shortcut for all of this. Since binary, octal, and hexadecimal are really all just powers of 2, octal, of course, is base 8 or 2 to the 3rd. Hexadecimal, which is base 16, is really 2 to the 4th. There's a nice relationship that exists between binary, octal, and hexadecimal. So there's a shortcut way of converting, and really all you need to do to go from binary to octal is group your binary bits or binary digits in groups of 3 and convert each group of 3 to one octal digit. So here I have a group of 3. This is the ones place, the twos place, and the fours place in binary. 4 plus 1 is 5, so that is a 5 in octal. The ones place, the twos place, the fours place, 2 plus 1 is 3. That's a 3 in octal. The ones place, the twos place, the fours place, that is a 2 in octal. So this number in binary is the same thing as 235 in base 8 or an octal, and we can convert back the other way. So let me do that. So I have 235. Each octal digit converts to 3 binary digits. So there is a 5 in binary. Well, how do you make a 5? 1, 0, 1, right? The ones place, twos place, the fours place. How do you make a 3? I need to make 3 digits out of it, so I need a leading 0, then 2 1s. Now I need to make a 2 in binary, so that is, of course, just 0, 1, 0, and I converted back to my base 2 number, which, of course, is the same number that I had over here. So hopefully that shortcut makes sense. Let's talk about converting from hexadecimal to binary and back. It's a very similar process converting from binary to hexadecimal, except I make groups of 4 because 4 bits are the numbers 0 to 16. I'm converting to base 16 here. So I consider each group of 4 bits as its own separate hexadecimal digit. 1, 2, 4, 8's place. So I have 8 plus 4 is 12, 13. This is a 13 in hexadecimal. And let's do the next one. 1, 2, 4, 8. 8 plus 1 is 9. This is a 9 in hexadecimal, but of course I can't write 913. I have to convert 13 into its correct hexadecimal symbol. And remember, it goes 0, 1, blah, 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 up to 9. Then 10 is an A, then B, C, D, E, finally F. So what is a 13? Well, that's 10, 11, 12, 13, 14, and F is a 15. So a D is a 13. So this is the number 9D in hexadecimal or in base 16. And of course, you can convert back if you take each hexadecimal digit and convert it to 4 binary digits. A D is, of course, a 13, and we have it above. A 13, of course, is 1, 1, 0, 1, and a 9 is 1, 0, 0, 1. So you can convert back into your binary number from base 16. All right, hopefully that all makes sense to you. Let's do one last big example where I give you a decimal number and I will convert it to binary, octal, and hexadecimal. And I'm going to use the shortcut as much as possible. And this is actually how I would convert a number from decimal to all of these other number systems. I don't use the repeated division. I find that it's error prone. It's just easy to mess that up. So how would I go from base 10 to binary? As you know already, I just draw a bunch of dashes and then I put the place value underneath them. This is the 1's place, the 2's place, the 4's place, the 8's place, right? This is binary. I'm just doubling. 16, 32, 64, 128. That's far enough. I don't need any 128s to make an 85, but I need a 64. So 85 minus 64 is 21. All right, so I have 21 left. I'll make a note of that. That's nothing in the 32's place. I need a 16. 21 minus 16 is 5. All right, so I have 5 left now. I don't need any 8s. I need a 4 and I need a 1. And I could just check this, which is what I usually do by adding these up. 64 plus 16 is 80. That's 84, 85. So that worked. So my binary number is 1010. I'm getting myself mixed up here. 101. Have I got the right number of zeros and ones? I think so. 101, 0101, 101, 0101. Well, that was sort of not the best choice, but that's all right. So this is my binary number. And now I'll just convert it to octal and to hexadecimal. So let's do octal first. I just group it in 3s. So that's a group of 3. That's a group of 3. My next group of 3 is going to have some leading zeros. So this group of 3, I just have the 1's place, the 2's place, the 4's place. That is a 5 in base 8, octal, right? Then I have the 1's place, the 2's place, the 4's place. That is a 2. The 1's place, the 2's place, the 4's place. That is a 1. So that number in base 10 is 125, or 125, I should say, in octal. And I could also convert it to base 16. Let me just recopy that. So I have 0, 1, 0, 1, 0, 1, 0, 1. Now I'm going to base 16. So I just group it by 4s. 1, 2, 4, 8. So that gives me a 5 in the 1's place. And then I have the same thing again. 1, 2, 4, 8. So that gives me a 5 again. So this number in base 16 is 5, 5 in base 16. So when I convert from base 10 into another base, usually I first convert it to binary and then I use the shortcut, either group it by 3s or group it by 4s, to go into base 8 or to base 16. Now if I'm going the other way, if I'm going, let's say, from base 16 to base 10, I do use the weighted multiplication. I know this is really a 5 in the 1's place. I know this is really a 5 in the 16's place. 5 times 16 is 80, so this is really an 80. 5 in the 1's place is 5. I just add those up. So there is my 85 in base 10. And I could do the same thing for 125 base 8. That's really the 1's place. The 8's place. 8 times 8 is 64. That's the 64's place. So I have a 1 in the 64's place. A 2 in the 8's place. 2 times 8 is 16. A 1 in the 5's place. So 64 plus 16 is 80, plus 5 is 85 base 10. And so hopefully, I know we've gone through a lot here, but hopefully you have some sense of how to convert between decimal, binary, octal, and hexadecimal. All right, good luck.